Hello, welcome. And let's continue with the topic that we had, that realizability thing. So you remember what I said, right? So we had some sort of semantics for first order constructive arithmetic based on recursive functions. And then the whole idea was that you can prove some independence, like that some weird things like some usual things like excluded medial could be just unprovable. Some weird things can be consistent, like assuming that every function is computable with constructive arithmetic, something that is inconsistent with classical arithmetic. And then also you can use it to extract information. So then I said that that is just for arithmetic. Is it possible to do it for any set, some sort of set theory based on that computational content? And then, of course, since Topos theory is our model of that thing, of constructive sets, so my intention is to construct one Topos, right? So how to do it? I said that Dana Scott had the idea that you can read realizability in terms of some sort of weird alternative truth values that you assign to your formulas, right? So the idea was, if you remember, something like that you have your formula, let's say that it is arithmetical, and then the value of it should be all the n's that, or all the r's, this is my notation last time, that realizes A, right? So some time ago, we had just the truth value all the time moment, the temporal moments where the guy is true. Now all the constructions of it or whatever, right? That's a reasonable thing to do. And then if you follow that idea, then you get uh, these things. Because this guy lives in Pn, power set of n. So then if and your guy is what is a sentence. So if you start with something with k many variables, like, then the value should be what? Should be again the same thing, but now the guy is depending on the tuple n. Therefore, yes, this guy is here, but if you think of the value as, you know, something variable in terms of n, then the guy lives actually in Pn to nk, right? So therefore, this is my values whenever I'm working with k many variables, right? And I said two things about this guy. So it's a pre-heighting algebra. And pre-heighting means it is just heighting algebra, but not really a poset. It's a pre-order, right? So the only difference is that, if you have A less than B and B is less than A, then you don't have it. You don't have antisymmetry. But that's the only difference. But you have also conjunction, disjunction, etc. in the obvious way. And if you remember, I said two things. One is that even when you work with Pn, and then you have two subsets, the order here is not the usual order of subset. It is subset up to recursive, change. So this simply means there exists a function, recursive. So let's say even partial recursive. So, partial recursive such that for any A in A, f of A is defined and it is in B, right? So I say A is less than B when I have this. And then you can see that it is really a pre-order because it is possible that A is less than B, B is less than A, but they are not equal. The second point is it reasonable? Yes. The second point was that when you go from Pn to Pn to n to the k, then the order is not pointwise. That you have two things like this, and then you say that this is less than b of x whenever it is less than that for any x. It's not pointwise, it is uniform. So meaning that if I have one element here, and probably I can write it like px as a function that reads x here and then computes something there, then I say this guy is less than this guy uh, if there exists again a function, partial recursive, let's write like this, such that for any x, in this case in nk, and for any a inside p, let's be, that could be ugly, f a holds and it is inside p. So my point, I'm not sure, inside what? Q away. So my point is that this guy, f, really depends on your A element here, right? It is just seriously uniform in N. So therefore it is not pointwise. We had these things, and again remember that this is just realizability, changed to be some sort of alternative valuation. So now this should help us to see how to generalize it. Yes. So I have two elements here, meaning two functions. And I say that one is less than the other when there exists a partial recursive function on natural numbers, such that for any n, for any element for these two guys, for any a, if you start with the first guy, f of it is in the second guy, and it always holds. But the point is that f doesn't depend on n. It is just uniform. You find a way to go from Pn to Qn in a recursive way that works for any n.
Okay. And you're saying this is not pointwise?
No.
What would it be pointwise?
Pointwise means that for any n, P is less than Q, Pn is less than Qn, meaning that for any n, there exists a function. So this is there exists a function that works for any n. Yes. Yeah, pointwise in the sense that it is not with respect to that one. Yes. Okay, so but everything is just arithmetic, and arithmetic is here, right? So because parameters comes from arithmetic. So you can change it to define a topos like this. That the idea is this, that you define, probably I have to start here. Before going to the topos, the generalized version of this argument here, or this kind of definition, is that of course I can change it to any set X, right? And I say that Pn to X is a set, and the elements, the order is defined exactly like this, but let's say that for any, I don't know, X is in X, right? Simply because, who cares? No. P of anything in X lives in subsets. Fair enough. So let's say that two predicates QR, and then I mean here Q, and I mean here R.
Map to the natural numbers.
Yes.
And the reason they're mapped to the natural numbers is because that's where you realize that.
You can just forget about realizability. The point is that everything is a subset of it. Right? So you have QX, you have RX, they depend on X, but when you fix your X, they are just subsets of Pn. And then what I'm saying is that there is some recursive function that maps this subset to that subset, regardless what the X is.
Yeah, working towards is do you need to consider recursive functions on arbitrary sets and not just on numbers?
I see, but No.
Because I'm really standing in for the code's recursive function. That's the most important use in real.
That is true. And also one important thing to mention is that this function f simply depends on a, which is a natural number, but not an x. So it is uniform because otherwise I cannot, find the meaning of it. So this guy with this order is a pre-Heyting algebra. And if you want to know the Heyting algebra structure, it is already there, right? Via that realizability. So for instance, if I have some Q and some R, two elements here, then this guy should be another subset depending on X, right? And okay, probably this is misleading. So this guy should be a function, right, in terms of X, and it is simply just the pairs of all R0, R1, such in N, of course, such that R0 is in QX and R1 is in Rx. Right? I claim that if you complete this guy, then it is, of course, it depends on X, right? It's another function, and it is really the meat here. And the join.
Definition of the algebra, or is it
What do you mean? So yes, it is my definition, but at the same time, it's not arbitrary because yeah, it should be that meat. So it is. Let's say that it is my description of the meat, and you can do your join, of course, right? Again, according to that realizability idea, right? Again, pairs in N such that either R0 is 0 and R1 is in QX, or R0 is not 0 or it is 1, depending on your favorite type of thing. And then it is in. That is Q. And then you have your implication, etc., right? So these are all the codes in N of Turing machines that map QX to RX, right? And so that's it. And so you also need the the top and the bottom element. So we have to move here then.
All right, just reminding myself of your definition of realizability.
Right.
So your recursive functions, they never need to actually produce anything in the structure.
What do you mean in the structure?
Well, so your definition of realizing well, you define it for natural numbers.
Yes.
And your definition of realizing the atomic formula is just the atomic formula is true.
That's true.
So it's not like we need to produce some 50% here.
Yes.
The place you do need to do it is just in this definition of implication, say.
And also conjunction, disjunction, yes. Yes, you can start with anything as long as your atom is true.
It's just that your realizers are always some machine that outputs some other machine.
Not necessarily. So sometimes they could be just pairs of two machines.
Okay, there's always some code machine. It's always only talking about machine. So the thing the machines are actually talking about. Well, the only thing that's not a machine.
Yes.
Is this 0 and 1 right here, I think.
And also the pair. So you don't accept this guy as something legitimate. So if you want to have conjunction, then it's a pair. Disjunction is also a pair. Yes, the main thing is this guy, which is a machine. But if I have just Q implies R, or I don't know, Q prime implies R prime, then it is a pair of 0 or 1 and one machine. Right? So you can build up over a machine.
Okay, so nothing from the structure, just these zeros and ones and machines that talk about zeros, ones, and pairs.
Yes.
Okay.
So then, of course, because it is the pre-Heyting algebra, and I guess we have to move to this board. Then what is top? Top should be top x probably. It depends on x, but it doesn't really. So it should be just the biggest possible of all, meaning n, and the bottom should be just empty, right? So yes, they are top and bottom in the usual inclusion order, but also in my weird order, right? Because there is always a function from empty to something and something to empty. So I don't check, of course, but you can check that Pn to x for any set n, set x, it is actually the pre-tightening algebra. Okay, fair enough. So then what is an this guy, antisymmetry? Because it is possible that I have any two singletons can be reduced to each other, right? Okay, so it is possible to make everything by quotient to be just real Heyting algebra, but then the problem is that it gets ugly because everything, so they are not functions, they are quotients of functions, right? There are two types. So one is easy for something, the other is easy for another thing, right? So that's my choice to work with pre-Heyting algebra, but sometimes people work with Heyting algebras by quotients, but then you have to be careful about other things. Anyway, what is then effective set? Or an effective set, and effective is for that computation kind of thing, is a pair of a set and a relation R, and I'm copying that H set thing that we had, such that R lives inside Pn x times x, or if you don't like it, or equivalently, it is a function, right? So it's a function, therefore I can simply write it like this. And there is a reason that I like to write like that, but we'll see it later. But still, it's a function, but not any function, such that you have these two properties, of course, like the property are, because this is just equality, right? So then they should be what? They should be not the others. Symmetric and transitive. So what does it mean to be symmetric and transitive? It means this. And transitive means this. But you have to be careful. What do I mean by that? I mean that don't read these guys as pointwise. When I write this, I mean R as an element in this Heyting algebra. This guy is another element in this Heyting algebra, reading two things and computing Pn. And when I write this order, I mean the order here. I mean that order there. I mean you have to, so this simply means there exists a computable function such that for any x and y in a uniform way, for any a inside R of x, y, you compute f of a in R, y, x, right? That is what I mean, really. So it could be confusing simply because there are two things. As I said, this guy is just a set of our functions. But when you have the order, it is not pointwise, right? So when you define things, it is pointwise. When you have the order, it is not pointwise. And sometimes it gets confusing. So whenever I write something like this with some variables, I always mean that put all the variables like x times x times x or whatever, and then the order is there. And not just the order, this conjunction is also there, right? So by this, I mean there exists a function g such that for any x, y, z, fair enough, and for any pair of two elements, right, a, b, such that a is in the first and b is in the second, then I can compute something in the right? So this is also not the usual intersection or whatever. You have to be careful always that what we mean really by these things. But the good thing is that we can pretend that we are doing some logical thing, right? This is good for intuition. Okay, so whenever I have this thing, then it is an effective set. One obvious effective set that you can work with always is that you can come up with, you can transform any set. So let X be a set, any set. Then there is a canonical way to construct an effective set, right? And then the canonical way simply is that consider X and say equality on X as before, and then equality of X simply is a function from X to Pn, and uh, it works like this. That so the value here is if they are really equal, then n the top, otherwise the bottom. So that's just obvious, right? And you can check that you have all these properties. But again, just to emphasize, here, for instance, if all the three are equal, then to witness it, you need a function from n times n to n, and you can always construct it. It is just enough to have projection or whatever. That is easy. One non-obvious example probably is the one that we started with, the n, but I have to interpret it in this way. So let's call, so n for me is just natural numbers with some equality, some canonical equality on n. And that canonical equality is this. So m equals n over n. So that should be a subset of n, right? What is this subset? It is not like this, that either they are true or they are not true, and then you have all and none. You have none here, but here you have just singleton m. Right? So what I'm saying is that if two things are not equal, okay, whatever, empty. But if they are equal, the witness is not anything, it is the number itself, right? So I have access more. When I have a proof, I know what kind of equality I'm proving. It's not just, you know. Does it have this property? Then yes, because this is just identity function, and this is just projection, right? Because the only non-trivial case for this guy is that all of them are equal, and then this is just this is, all of them are equal to n. This is n, but it's a pair, so it's just enough to do the projection, right?
Realizability in some way, or if you realize of true equality.
Yes, we can. Yeah, there are many ways to define our reality. Not really. So the point is that it is kind of arbitrary, and some are easier to work with. This is one of the easier ones. Yes. So, but to define this, there is a serious reason. So it's not arbitrary, as I explained in a moment. So, okay, fair enough. Question is that these are our objects. What are our morphisms? Right? I have to come up with my morphisms. So morphisms are again like H set with a bit more care, right? So what should be a morphism from X R? So these are two effective sets, some F, right? Of course, it should be a relation. Relation in this case means a function from X times Y to Pn, but not anyone with the conditions, right? The condition that's functional, it is total, it is well-defined, right? And all the conditions you have to write like those conditions, right? So for instance, what is being well-defined? So being well-defined means one, that if you have fxy, then so as usual, of course, I didn't say it, but you don't have reflexivity, then Rxx is just the extent to which x exists. And also maybe intuitively it is good to read that Rxy is a subset of n by definition, and you read that subset as all the witnesses of this equality, right? So therefore you have to have this Ex, and you have to have this E1, right? So if x goes to y, then both of them should be defined. And so these two guys probably like this are being well defined if x1, x2 are equal and y1, so S probably y1, y2 are equal, then you have f x1, y1, then you have f x2, y2, and then also, so you respect equality. And the second guy is that it is functional, meaning that x1 and x2, if both go to y, then these two guys should be equal. No, come on, no. Sorry, y1, y2 for same x, then y should be equal. And the third, the totality is that E of x, if x exists, then you are less than this guy, of x, y. So there is some y such that blah, blah. So what I'm saying is that, again, remember, these are not pointwise in x and y, right? So by this guy, for instance, I mean this is subset of n, this is subset of n, this is subset of n. I mean there exists a function, computable function, that reads the witness here and computes the witness there and the witness there, right? A pair. So by this I mean pair, by this I mean uniform transformation via functions. It is not pointwise. And the same here. So you read some witness here of the existence of x, and then uniformly, without reading x itself, just the witness, you find the y. That doesn't matter, but you find recursively an element here, right? So, yeah. Okay, fair enough. So that's the definition of a map as before, with a bit of, care that everything should be uniform and the order is not subset, etc. But everything should be fine, right? So then probably I have to mention what should I do? Okay, one thing that I can do, probably this lemma is good to prove. It helps. So my goal is to come up with, to investigate at least two cases. All the maps between, two effective sets coming from set. So you have x and y. The intuition should be that if you go to x equality and y equality, then all the maps are in one-to-one correspondence with the maps from x to y. And probably something similar for n, right? To that characterization of maps, because come on, that definition is not clear. I need a lemma, and before the lemma, probably a definition. So the definition is that there are so many subfamilies or subcategories, if you like, of this this effective thing. And so we saw, for instance, one, but there are some, and one which is interesting is that something that people call assemblies. An effective set XR is an assembly. Sometimes people call it, I guess, separated. If you have this property that if x does not equal to y, then Rxy is empty. So you don't have any false proof, right? If two things are not equal, then there's no proof of it. In general, it could be possible, right? In general, you can simply define Rx and any y, everything, as just always n, right? Fixed n everywhere. So you believe that everything equals to everything. That is possible. Also, it somehow doesn't do something. So if two things are equal, then Rxy, which is exactly Rxx actually, which is E of x, it is non-empty. So if two things are equal, then I have a proof, at least one, right? So this guy These guys called assemblies. So if you think about it, assembly is simply just the E function, right? So that is always empty. So you have to just, for any x, say what is your E of x, and it should be non-empty. That's the thing. Rxx. The proof, yes,
And here, truth value is a subset of natural numbers,
yes,
which actually is a set of programs.
yes. You can read it as all
When you say
proofs,
EX,
programs, whatever.
you say EX, saying it's some proof or program that does something.
That witnesses equality of x to x. Yeah. And if they are not equal, then I have no witness of it. It's kind of sounds weakly complete. It's part of the definition.
Definition.
It's the intuition that R stands for equality.
That's the definition of the real life.
Yes.
This is not quite that, right? This is
No. Just forget. Realizers is a motivation for this guy for a moment. So now everything is just formally defined like you have one set, one relation. Relation means function from x times x to Pn, such that blah blah, right?
I guess my question is there some language where you mean this is meant to be some arbitrary thing or some set?
Yes. Could be any assignment, binary assignment of power set of subsets of n to the pairs.
First order form.
Yes.
What do you have now?
And now just forget about it for a moment. We will come back to it, that there is a connection between the two. But for now, what I have simply is that I have just one set, one function from x times x to Pn, such that I have these two properties and nothing else. But the intuition is that you can read Rxy intuitively as the set of all programs or witnesses for or proofs for equality of x and y.
Well, okay, it's just that I would be happy if there was some structure in the background where I knew what equality meant. So here, equality is just as members of X, some abstract way. And all the, you here have a language of talking about equality,
Yes.
but not really for anything else on X.
Yes, yeah, you have just it is just pure set, let's say. You have just equality and nothing else.
All right.
Yes. So it's far from arithmetic or what, but yeah, just pure set. Okay. Because we are constructing topos, right? It should be just a model of sets, not more.
Well,
there is one that E of X is some sort of membership, but not explicit. So, okay, that is assembly. And if you think both of my examples are assembly, right? So this guy is an assembly because it is empty, and whenever they are equal, it's non-empty. And this guy is non-empty, empty, right? So both are assemblies. And then the dilemma is that if these two guys, whatever, two parts. Why not? Let X R and Y S be assemblies. Then if F is a function from X to Y such that it respects E, because E is the only data that you have here, meaning that EX is less than E of F of X, then we can define Fxy simply as, S, why not? Can I be no? Or I guess S of F of X and Y. I guess that works. Then F is a map. So what I'm saying in the first part is that if you have you have some two assemblies, right? If you have a function, usual function, such that it, yeah, if you have a function such that it respects the equality, if you start with the existence of x, then you end up with the existence of f of x, then I can define f of x y, that x goes to y as f of x is y, according to S of f of x and y. Then that's a function in that way. So it's a way to transform any function to a morphism, let's say, right? That is easy. Yes, it's a map, effective map between effective sets. Morphism, yes. Morphism, map, all equivalent. So that I won't prove, but please believe me, that is true. What I want to have is the converse, actually. And the converse should come here, yes. Where is it? The converse is that if you start with what? If you start with your assemblies, then the part 2 of lemma says that for any, or I have to write that any f, any morphism f between the two say comes from a unique, or unique, I'm not sure, unique, huh? From, at least that is what I might need, from a function f. Right? So what I'm saying is that all the maps are constructed like that, as long as I have assemblies, right? And then that gives me a handle, right? That I can just forget about the things and go and check the sets such that you respect the existing. And the second part to prove is kind of interesting, and I want to do it. So I have to find my function f. So here is the observation. So the proof is that for any x, there exists a unique y such that fxy is non-empty. And define your y, f as that y. Right? How do I know this? Based on the conditions of the f there, right? So what I know is that first I can prove that there is at least one, right? Because otherwise f of x and any y is empty. And then the last guy would be ex is less than union of all y's fxy, which is just empty. But E of x is not empty because it is what? It is assembly, yes. And so this is non-empty, and that is impossible, simply, right? There is no function between non-empty to empty. Uniform, non-uniform, whatever. So that's obvious. Uniqueness is also obvious because if you have x and y and x and z, then you have this, right? S, y, z. But the point is that if y does not equal to z for different things, then this guy is empty, again, because I have assembly, right? Two different things cannot be equal. And if these two guys are non-empty, then the whole thing is non-empty, and I cannot go from non-empty to empty, right? Therefore, at most, one of them is non-empty. And that proves the uniqueness, right? And then you can simply define f as f of x is this exact y. And I guess that uniqueness also comes from this. And then that condition also important that this f respects E, the existence, and that comes from this, right? So E So you know that E of X is less than the union. There is exactly one Y such that it is non-empty. So I can forget about all of them. That one Y I defined as F of X, right? So E of X is less than F of X, right? And this is less than F of everything is less than E of the second guy. So I have the respect, right? What do you mean?
It seems to me that you argued that because the right-hand side is empty,
Yes,
it's not possible that both are not empty.
yes. Because if both are non-empty, this is not intersection, it's product, right? So
It's not-
yes, therefore it is non-empty if both are non-empty because it's product.
it's not-
No, it is the join in terms of that P to thing, and then we had it, right? The join. So this is meat, but meat here is just, yes, no, meat is just the pair. So the all the things are living here, right? So what is it? X, Y, Y, something of this sort, right? Three variables with different things. I don't know why, probably. And then in these types of guys, when you have two things like Q something and R something, we saw that this guy is actually the pair of R0, R1, such that the first is in the first and the second is in the second, right? So based on this, if these two are non-empty, then this is also non-empty because I can pick one element here, one element here, and then pair them up. So yes, so that intuition that could be confusing because we can have two sets with empty intersection. And this is important. This is you cannot do it with H sets, the one that I explained, but you can do it here exactly because of this property. So anyway, the point is that if you have assemblies, then you can say that always there's a function behind, and that the function respects E, right? And there are other things that you have to prove, but I don't care. If I come back to the two examples that I had, then I can say something interesting. What is the interesting thing? So first, what happens to sets? So let's say that X and Y are sets, and I have X equality and Y equality. And what are the morphisms? It is observation. That if X and Y are two sets, and then I have these two effective sets, then what are the maps between them? They are in one-to-one correspondence between maps from X to Y functions, such that they respect existence, and existence is just obvious, right? It's just either N or it's always N, actually, right? So always you respect it, therefore it is just a function, right? So this is in one-to-one correspondence with functions from X to Y. Maps in effective sets between the two is in one-to-one correspondence with functions from X to Y. And that means that actually we defined a functor from set. So one thing that I didn't mention, and I assume that it is obvious, but I had to say that this guy is the category of effective sets and the morphisms. To be a category, you have to have composition, right, between those maps and also identity, but you can come up with them, obviously. Composition is just the obvious composition of that functions, similar to H sets. And identity from XR to XR is just R, as before. So that's easy.
Sorry, this FF
Is the category
category effective set,
and those maps.
which is the thing.
Yes. And what I'm saying is that there is a functor, of course, that maps any X to this guy. and any function to that function between them. And this guy is actually full and faithful. So you don't map two morphisms to one, and you don't create any new morphism, right? So set really sits inside EFF, right? The effective. So that's, by the way, is effective topos is this guy. So technically, then I have my effective topos. We don't know that it is a topos yet, but anyway, set lives here, fully sits inside the effective topos. The other thing that the other observation that we can have is that what happens to the maps from our N to itself. It's also an assembly. So what are these maps? What do you think? What should be the maps from N to N? Of course, they are functions from N to N to start with, right? Something such that you respect equality, right? So there are functions that we know. Okay, fair enough. Such that you respect equality, meaning that EX is less than EFX. Again, millions of times. This is not pointwise, it is just uniform, right? Okay, so both of the E's are E with respect to N, and we know what they are, right? So this guy is a singleton X. This guy is a singleton F of X. And what does it mean? It means that regardless of X, there is a recursive function from this to that, right? So what I'm saying that there is a recursive function G that reads X and computes F of X. Simply, I'm saying that F is computable. Therefore, all the maps are just total computable functions, not all functions, right? So you can see that I'm doing something crazy here, right? It's a merge between two different games. Either you are working with the usual sets, and set simply sits here. So if you restrict yourself here, it is just a pure classical set theory. On the other hand, there is some N here, at least, copying from realizability. And here, every morph from N to N is just in one-to-one correspondence with computable functions. So around this N, everything is computable, but the whole effective set is not really computable. People usually say that this is just the computable word. That's true, but not really. Because it is not there. For millions of reasons, but one is by definition, right? So everything.
Well, same definition meaning equality in these two.
Huh? No, because the equality here means that if one thing equals to itself, the value is n.
Okay, but there are different types. There are sets of objects. Okay.
Yeah.
So you will have something like n inside set.
Exactly.
But not this.
No. Yeah. I have some n-like thing, right? Some prime, let's say, that this guy says that for if two things are not equal, then empty, but if they are equal, the value is n, the whole set. And there is also another n here. This is the real n, this is the fake n. And how do I know it? Because this is the natural numbers object. It has the induction that it should have. So the good thing about the category theory is that it says that so usually we say that this is the right thing, this is the wrong thing, right, in mathematics. And we know it because it behaves like as it should. But here I know what that behavior is, and then therefore I can formally say that what is right, what is wrong.
So can you remind us it's effective Topos?
I kind of define. It is category. This is effective.
Category. Objects in it.
No, this is effective topos, but I didn't prove that it's a topos. For now, it is just a category.
Okay. The objects in it are these pairs.
Effective sets, yes. Are
what is it?
X is a set, any set. R is that function with that property. Morphisms are those guys.
So those it's a collection of objects.
Who?
It's this thing you're trying to circle it and set. Your image of set, the image of set that you found inside.
Yes, it's a pure class, proper class. Yeah. And the whole thing is big, right? Huh?
When the equals x and equals y, it's doing the same thing as equals n, right?
No,
This, no?
no. There are two different equalities on n. This equality, yes, it is the same as equality here, right? This equality prime is that
Oh,
the value is
This
n.
is the old equality.
Yes.
Oh, wow.
This equality is that the point is that in this equality n equals n, the value is actually capital N. No, sorry, the singleton n. The other one, the one from set, the one here, right? So we have to say it prime, say. Yeah, of course, because I don't need it just to mention, but this is the only thing that I care about. There's just one n. Yeah? Okay. So what should I say? Probably since we are here, I have to say that this n also comes with two morphisms. So whatever. This category has at least the terminal object, right? The terminal object, it is easy to prove that it is the terminal object of this guy is simply a singleton star and this singleton star. So simply just this set, right? Star and this equality means that if it is between star and star, because it cannot be anything else, the value is simply total n, right? And nothing else. So this guy is a terminal object. And that's good, one thing. The other is that that n that we saw is a natural number object. Therefore, it is the right. How do I know that it's a natural number object? Because you can just prove it kind of easily. I don't bother to do that. But at least I have to explain the structure. So n, we had is n, an equality of it. I need two morphisms, one from n to n, one from 1 to n, right? That should be my 0, that should be my successor. 1 to n, it is enough to come from what? From one, whatever. So I just say it, and then let's say that's a 0, this is successor. This 0, simply the idea is that it should go from I didn't actually explain those things, but okay, whatever. So I can define this. So this should go from, this should be z of star and n, I have to define it, right? And simply it is just if n equals 0, it is just 0, and otherwise it is empty. And my successor is, so there are millions of ways that you can define it, but let me do this. So n and m is that if n plus 1 is m, then singleton m or empty otherwise. But there are equivalent ways. So one thing that I didn't mention, but probably I should, was that if you think about it, when I have two morphisms from xr to ys, right, it is possible that you have two morphisms, and any morphism is, as we saw, some function from x times y to pn, right? But sometimes they are equivalent, right? Because, you know, as elements in Pn to x times y, sometimes it is the case that these two are equivalent. But again, it is not pointwise. But they are not equal as subsets because, you know, for obvious reasons that everything is a pre-order. So whenever I have f equals to g, I consider them as the same maps, really. So everything is up to this equivalence. You have to bring it everywhere, but so for now, I don't care. For this reason, you can define it in different ways, right? In an equivalent way. So for instance, you can change this n to pair mn because you simply care you have to have all the information here. Here it could be 0 and I don't know. No, okay, here it should be 0. But here it could be any event, mn, pair of them, I don't know, whatever. So as long as you can, in one-to-one way, must be computable, exactly. Forward if you go there, but backward if you go, but everything is easy, right? So to see. So anyway, this data with these two guys is a natural number object. And why is it important? Because if it is a natural numbers object, then you can do your, arithmetic inside the topos. But for me, it is important because I want to prove now so still we don't know that it is a topos. I will show that it's a topos, but this guy is not Grothendieck, meaning that it is not equivalent to any CJ thing. So it's a very new topos. And we had some example of non-Grothendieck topos, right? It is just finite sets. But it was not Grothendieck simply because it's too small. This guy is not small. It has a copy of sets inside it, beside. Just big. But it is not Grothendieck. Right? Kinda, it was the first example ever of non-Grothendieck topos that Highland came up with. And the reason is this, that in any Grothendieck topos, natural numbers object is actually nothing but co-product, countable many, aleph self many, aleph zero many, addition of 1. 1 plus 1 plus 1, 1, right? Like in set. In set, if you have one star and you do your disjoint union, you get your n, right? And the same is true for any category of shapes. Always you can compare. But this is not true in effective topos. Why? Because it is restricted when it comes to n. How do I know that? Let's say that it is true, right? Let's say that here in effective topos, I have that infinite coproduct, and then it is actually equivalent to this n that I have, right? Then something bad happens, and that bad thing is this. That things. So what are the maps from n to n? On the one hand, we know that they are in one-to-one correspondence with what? With all computable functions, and therefore it is countable. The number of maps between n and n, right? If n is this guy, then you have 1 plus 1, etc. to n. So the maps are in one-to-one correspondence to maps here, but this is just coproduct. So it is in one-to-one correspondence between a sequence of maps from any 1 to n, and these are uncountably many, right? Because, each of them is 1 to n. You are picking one element, right? And then there are, so just there are too much. So that is the thing. The thing is that n is kind of restricted actually here. So it's not a Grothendieck topos. And what should I say then? So, but we didn't prove that it's a topos, right? And I shouldn't even. I have to say, however, something. There are many things that I have to say. So one thing that I have to mention is that it is a topos. And to prove that it's a topos, you have to prove that the finite limit, exponentiation, sub-object classifier, right? And who does it? Right? So just believe me, there is the things. But one thing that I have to say, okay, we had the terminal. For product, at least I have to say that product, what is product of this guy and that guy? It is just this, x times y, and r times s, but with a bit of care. So this is just the usual product. R times s should be a map from what? From x times y times x times y, square of this guy, to Pn. And then you may say that Rs of x1, y1, x2, y2 should be what? Equality of these pairs should be equality of the first and the second. So therefore you may say, times S1, what is, but it should be it should be subset of n, right? Here by times I simply mean the pair of elements here and the elements there, right? So you do that trick and then you can do your 8-set thing. It works. So that's a product. But for the rest, probably it is better to say something interesting. So that interesting thing is that we saw that any Pn 2x is a pre-Heiting algebra, right? We started here. We picked one element in Pn to x times x as the equality. But there is more actually. So it's not just some, for any x, there is one pre-Heiting algebra, but there is a connection between them, right? And the connection is, one of the connections that I'm interested in is the quantifiers, right? So if you go from this guy to that guy with projection, then of course you get a canonical map from Pn to x to Pn of x times y, right? Like Bart. So this is a map from x to Pn. You compose it with this guy, it would be a map from x times y to Pn, right? Suspicious?
The other way, well, I don't expect.
Yeah, the point is that in x it is contravariant, right? So this is a map from x to Pn. You start here. So x to Pn, you compose them, then it would be x times y to Pn. So with composition, you come in this way, right? And so this is exactly like that. You have a predicate with one variable. You pretend that you have it with two variables, as we had before. And if you think about it, you have adjoints. Two maps. There are two maps in this way, like existence and for all, such that it copies the intuitionistic behavior of the quantifiers. So what do I mean? I simply mean, so probably I have to define it even. Adjoint. Left and right adjoint. So let me just describe them. So the description is this, that you start here, you have some qxy, you want to put their exist on something, and that something is the one that you want to forget, so the exist y. By this guy, which is just this map over q, I simply mean that union on x, union on y, not x, sorry, qxy. And for all simply means intersection, as you expect, right? So this is just not arbitrary things that I'm defining. Adjoints are unique, and if you think about them, then it is just this. And the reason simply is that whatever I'm doing is, uniform in x and y, right? So, and so that's fine. What is the use of this? This gives me like what I had for the Heiting thing, right? So I had the power to write all the time and or not. I didn't use or, but and sometimes implication, right? And now I have quantifiers. So I can pretend that I'm talking about actually some logical values, but actually they are about programs, right? And what's the use of it? The use is that it helps to describe more complicated things. Q is an element here, so it's a map from x times y to Pn. So this guy is a thing B. So how does it help? It helps with, with your limit, meaning your equalizer. It helps with your, I don't know, exponentiation, sub-object classifier, whatever. So for instance, let's say that what happens for equalizer, right? So it helps like this. You have two maps between x, r, and y, s, and you want to equalize. How to do it? Simply, again, like H sets, you go here, you change your r to r prime, the same x, and it should be H probably. And then what is r prime? So first you define existence, E prime. So something is something exists here simply when these two guys are equal, right? On it. So just write the value of it. There exists y such that fx, y, and g, x, y. Right? According to this guy, it's a value, right? It lives inside, inside P into X. Therefore, it is something reasonable to write down, right? It simply helps. So if you think it is just a big union and this is just a pair of two maps, two things, right? But I'm pretending that everything is logical. And when you have E prime, then you can define your R prime as x1, x2. Here simply is that these two guys, of course, exist, and they are equal according to x, right? But again, this language helps me, right? So if I want to write down every program, then here I have to say that this is a set of all numbers, actually triples of numbers. The first number uniformly does something, right? It is inside this. The second that, third that, right? So that's a way to avoid all programs when you design your theory and also use your logical intuition. And similarly, you can define H. H is simply x1, x2. So it should be just identity, but the first guy should come here. So this should be this, and just equality with respect to the bigger one, right? So you just write all the things that you expect. And it is equalizer. Or when it comes to exponentiation, you have ys, xr, and what is it? So we had the same idea as we had for H sets, right? So elements here are all possible relations in quotation, meaning that Pn to x times y, and some t, the equality. And what is the equality here? So the equality is between two things, right? 2f and g. So again, I came up with E. EF means that F is a map. So if you think about this, that F is a map, it was something that you can write with quantifiers and implication, etc., right? That F respects this, and F respects equality, and F is total, right? So you write a big thing. So for instance, F respects, so we had this condition, right? For instance. So this is one part of this game. For any x, y, it should be fxy implies ex. And something else, right? So the totality would be and. For any x, e of x implies there exists y, fxy, right? So as long as I have quantifiers, and I have the Heyting structure and or implication, I can write down something, right? And I put it here, and then ETFG should be EF, EG. So meaning that so this is all maps. So some of them are functional. So pick the functional ones, and they are equal. What is equality between two things? It is simply equal everywhere, right? So for any x, y, f x, y, if and only if gx. So that's the trick, right? So just imagine how hard it would be just to open up it as, codes. Triple of codes. The first code comes here, meaning that it is, I don't know, a tuple of numbers, each witnessing this means that, come on. So that works, and it is just exponentiation. That's good news. And why is it again? Oh, that's good. Larry. So, and what happens to sub-object classifier? What happens to sub-object classifier? So, sub-object classifier should be what? Should be the value, right? And what is the set of value? Pn. So then omega should be some effective set. The effective set is Pn. And what should be the equality here? It should be if and only if, right? As always. So that is my sub-object classifier. And so what is the map from 1 to omega, that truth map that I needed? So the truth map should be something from, so equivalently, it is just a map from Pn to Pn, right? It is Pn times star, which is Pn to Pn, and this is just identity. Equivalently, you are simply picking n from omega, right? And so that's a sub-object classifier. You have to prove it. Again, you have to do some tricks like what are the moniques? The moniques are effective subsets. What is effective subsets? What is an effective subset? So if you remember, we had it for those things for 8 sets. Effective subsets of XR are what? Are of course maps, say S from X to Pn, such that they respect existence and they respect equality. Right? Exactly like what we had for omega sets. I'm defining subsets, effective subsets. And then there is one-to-one correspondence between sub-objects and effective subsets. And therefore, you can use it simply to make this guy into your sub-object classifier. All in all, you can prove that this guy is a topos. But technically, we did more if you think about it. Yes, I avoided all possible things related to what? To do the computers. That I explained everything, but I didn't really, explain. But if you think about it, you see that actually it doesn't matter that everything is computable, really, right? So what I used is this. I used the fact that Pn to x, which stands for, the predicates over x, right? This is a pre-Heyting algebra. I use it everywhere. 2, I use that existence of quantifiers that I erased, right? The relation between Pn x times y and Pn to x, the two adjoints. And together, I have the power to write every first order sentence. And then based on those first order sentence, I did this exponentiation, I did sub-object. No, I did what? I did equalizers, I did, you can do the same for product, for everything, right? Except the sub-object classifier. You can do everything because simply we constructed whatever we wanted, right? And then we did what's needed. So for instance, if you know what I mean, right? So I didn't really use the information inside. I used the fact that it is a pre-Heyting algebra and there is some connection for quantifiers. So this led to a generalization of this game that Why not? So you can think that let's just forget about this structure and you say that I start with an assignment that maps to any x some what? Pre-heighting algebra. Of course, it should do it in a functorial way, meaning that when you go, so this means the power set of x, if you like. So if you go from x to y, then there is a map from py to px, right? And then this is one of the conditions. The other is that you have to be able to handle the quantifiers. Therefore, there should be a map from px times y to px, I guess, to as adjoints to the obvious map from, exactly the same thing that I wrote there. And if you have this, then you can define your p set instead of effective set, and it should be simply just x and r is an element in p of x times x, like that we had before, such that you have those two conditions exactly, and then you can construct a topos of it. P sets could be a topos, except that you miss the subobject classifier. For subobject classifier, you have to add also one more structure, and that structure simply is that you need a set and you need some generic predicate. So meaning that the other structure is that there should be one set sigma, one element in P sigma, like sigma, and this guy is the generic. So this, read it as, subject classifier and the truth value, right? And it is generic, meaning that everything is just the pullback of that guy. I'm not explaining the details of this, just to say that having this condition and having just reasonable assignments of pre-heighting algebras leads to a topos. And the construction is exactly the same as you had for effective topos and you had for H sets. They are actually two different versions of this, right? For H sets, you define Px as x as H to x, right? All the maps from x to your H. And here you define it as Pn, and these are not the same, right? This order is pointwise, this is not, right? But the point is that it is kind of this P is a generalization of that H value. So when you construct H value, you pick one values, and then from those values, you have the values for subsets, right? As maps from X to H. But this condition says that, okay, you can go for more general thing. Just axiomatize all possible power sets, not just the values, and then from that construct every other values. But of course, everything should be somehow coherent with each other. And it is not something, fancy that you don't need, simply because effective topos is one of them, and you cannot reach it from this structure simply because these are Grothendieck, effective is not. So it's a real generalization. It's important. Okay, so probably the last thing that I have to say, and I have to move maybe, is that what happened to our independence, right? And how does it have something to do with our realizability thing? So the point is that, as I said, so first, in any topos we cite, right? As long as E is a topos, we saw that we can interpret first order here, right? As subobjects of things. Okay. So therefore, if I start with arithmetic as a theory, meaning the theory HA, say, as we had before, then I can interpret it inside my topos, as long as I specify what is my type n, what is my natural numbers, right? And it is, of course, n, as we had before, right? It is the natural numbers object. So I pick n, and then whenever you have any formula, if you interpret it here, then you can see that actually you have to use quantifiers via that kind of thing. And so meaning that, in effective topos, so probably I have to say it here. So in effective topos, if uh, if you are here, if you pick some sub-object, some sub-object, so two sub-objects, whatever, one sub-object here, these are two objects, then what is this guy? And what is this guy? So it is good if we have a way to compute these two guys, because otherwise, for the others, we know how to compute, right? This sub is somehow related to that Pn to x times y. Therefore, we have the Heiting structure. These two are simply that for all x. So probably I have to say that for any x in x and for there exists x in x. So this means that for all, in the sense, the big intersection, Ex implies P x y, and this is exist x, meaning a big union, such that Ex. So you have to add your E here or there to have a reasonable first order, right? Because otherwise existence would be a problem, right? And then, so that is how to interpret quantifiers in effective topos. And if you come back, then to interpret arithmetic, then this is your n. And then, of course, I can write a formula. So phi quantifiers are according to this. Always this x is n, because everything is related to n. And then you have implication, etc., etc. So if you compute it, then there is a theorem. The theorem is that for any formula, phi n bar, phi x, let's say, you have this. The value of phi n bar, if you interpret phi inside the effective topos, as I explained, you get a value, right? The value is actually the set of all r's that realizes phi n. So that's a connection with realizability, of course, because we constructed it from realizability, right? And the good thing is that then realizability gives us really the computational way, like the forcing style thing, to really compute the value. One thing. The other is that if you think about it, we had something about our realizability before, like the Church-Turing thesis, like the excluded middle that is not true in our realizability, etc. So if you transform it to the truth value, then it would be that in effective, for instance, in effective topos, Church thesis 0 is valid. What does it mean? It means that the value of it is, true, right? So I constructed the universe similar to set theory and some natural number object somewhere that you can pretend that it is a model of arithmetic. And then in that model of arithmetic, if you interpret this statement, the Church thesis, then you see that it's true. It simply says that for any x, there exists y, phi x, y implies there exists E, the code of this, such that for any x, E dot x holds, and phi of x, E dot x. So more or less every function is computable, right? That is true. Or in EF, the same. There exists some formula A such that negation of for all x A or negation A is true, really, right? So seriously, the excluded middle is wrong in the model, right? So that's a just very reasonable model, but somehow when it comes to n, remember, you have also set theory living there inside set, inside F, right? Inside effective topos. So whenever it's related at least to arithmetic, everything is computable. And I didn't say, but there is some sort of double negation kind of thing that we had for Heyting algebra, you can have it for toposes. And then the double negation, the classical part of effective topos is actually that set part. So then when it comes to real classical, it is set. But then when you go up, you see that at least around n, you have just a universe such that something weird is true, right?
So if you did the double negation to this corollary.
Yes. No. Double negation of CT, you mean? No, it shouldn't be, I guess. No, it shouldn't. And I mean, no, here it is true. Inside this effective topos, yes, it is true. Double negation. So the guy is true. Its double negation should be also true. So no, that. Okay, it is not like that. You double negation things, right? It is something similar, but more complicated. So if you bear with me, just let me say what. Okay, no, let me just be here. And probably say something about the higher order quickly. So what's the point, right? You may say that, okay, we had the realizability. From realizability, you constructed some big topos, whatever. And then at last, as a application, you showed us that it is just realizability, and therefore you have all the things that you had from realizability. Okay. Yes, in some sense it is interesting because I constructed, one universe, and then computing the value of things is just like any other universe, right? You are not changing the semantics, you are changing the domain. But that is not very interesting. The main motivation that Highland had is actually to generalize this argument, this realizability style of thing, to set theory, to higher order first, and then, to power set to whatever, right? So, and the good news is that when you have a topos, any topos, we saw that how to interpret first order, but also higher order, I mentioned that we can interpret, right? So for instance, if you have the language of arithmetic, you have something like this, right? From type n. These are numbers. Usually you don't write it. But also probably you have some functions from n to n, right? Of course, I can interpret it inside the topos because I have exponentiation, right, inside the topos. And you can have some p inside, power set of n, if you like, right? I can interpret them. I can just iterate it, right, from n to n to n. So these things that are the things that I can have now in my topos, and therefore I have some sort of realizability kind of things for them. So probably I have to say that, so I want to mention just two things for this n to the n and this guy, just to have some cute things. And but one thing that, Merry Christmas, yes. We have to compute these two guys. We had a way to compute exponentiation. Of course, I don't do that, but I simply say what is it. So if you compute this, then it is equivalent to this very cute set. First, it is an assembly. Two, the set is the set of all total recursive functions from n to n. So this is my set. And I need just one E because it is assembly, right? So E is enough. So what is E of f of function? It is all codes of it, which is a subset of f. So that's fine, right? What happens to n to the n to the n? This is that. So the set is effective operations that I explain in a moment. And there is some E. So what is effective operation? So you know it, but effective operation simply is a map phi from recursive functions to n. So it reads functions one level higher. But effective means that yes, it reads functions, but it is actually computable. Computable means that if you think of it as a map over the codes, it is computable. So meaning that there is some computable function f computable such that what? Such that okay, f is bad. So there is some phi such that for any f, for any e code of f, then phi of f, if you compute it, it is just phi of e, right? Simply, I'm saying that, you know, just forget about recursive functions. It is, you know, working on codes as a recursive function. And any code of this recursive function is actually code of phi, right? That tracks phi. And then E of any phi here is the set again of codes of phi, right? So what I'm saying is that n has a meaning in effective sets. Exponentiation has a meaning. You can go and compute this, and then you see that these equivalences hold. And what's the point? The point is this, and I promise this is the last thing. The point is that now I can talk about higher order things and evaluate them inside my topos, right? The higher order things, one is, so we had CT0, but now we can have CT without zero, without pushing it to be first order. So CT should be any function is computable such that right. So you have to write it down in a way, and then so simply I'm saying that everything has a code, right? This guy is valid inside my topos, effective topos. How to evaluate it? The main idea is that if I want to evaluate it, I have to go for the way to read to quantifiers, right, in an effective topos. So if you read this quantifier, it is just a big intersection. It means simply for all. This means it exists. But the only thing is that you have E of f starting here. So the main thing is that you start with E of f, right? And then you have to go to something, but you have to also prove that E of E and something, right? That is the definition of quantifiers. So this is the point. So it is just for all f, there exists E, this, right? And etc. And this is something that if you work out the propositional part, you see that it is just simply easy to understand because E of f is just a set of codes for f. And now I have to come up with a number, and E of E is just singleton of number E. So what should be the function here? It is just simple. Read the code of f and compute itself, right? And of course, it does the same thing, right? So just map the code to. So the point is that it's for all, you need a computable function here, but it reads a code, not itself, and then compute the code here. The next thing, the last is Blower principle, that any function from n to n, any functional is continuous, meaning that for any n and any f, there exists some m in n such that for any g in n to n, if for any n, if f n, okay, probably I write it and I just say it out loud, it is easier. So what does it mean? So the axiom says that if you have some operations that start with functions and go to numbers, and you have some function, some input fixed, then there is some point that phi of f actually depends on those first elements of f, right? F as a function, as a sequence. And this means equality up to n, meaning f of n equals to g of n for any n less than n, right? So simply it says that phi is continuous, right? It reads f and compute whatever it does. It depends simply on the finite first elements of your sequence, right? If you do something with your sequence, if you are a computer or a human being, the only thing that you can do is just to use a first segment of your sequence, right? You cannot do anything more. So that's the thing. And this is also true in effective topos. And the reason is easy. So the reason is that, again, for all, etc., so you have to read this guy. You have to read this guy. And you have to compute your m, etc., right? That's your task. And what is the code? It's a tracker, as I mentioned there. What's the code here? Again, a tracker. And then you have to find m. So, but in a computable way. Everything should be computable. So I need a theorem from recursion theory. A theorem that says that if you read a code for phi and a code for f, you really can find m in a computable way, such that, etc. And there is a theorem actually in recursion theory. It's called KLS theorem. I guess Kreisel, I don't know what, and someone else, right? It's yeah. There is something that's called KLS theorem. Exactly this. That there is recursively it is continuous, right? So if you think about it, this thing that is kind of equivalent to the broader thing that all maps are real numbers of computable, which is are continuous, which is kind of nonsense. But you have to think about it in some, some other way. That yes, it is nonsense if you think classically, but it is not. It is actually describing something else. It is describing either continuous world or computable world, right? Not just the real world that we have. This is the classical point of view to these weird things. But anyway, so the point is that if you go for effective topos, the goal is that you can work with higher order things and refute higher order things from higher order arithmetic. And that's it. I'm sure that there is no. No, it's not the last one. What's the goal of this construction?
I kind of was wondering if you were aiming towards the axiom of choice, but you're not. You're doing effective stuff.
Yes. The axiom of choice is also wrong here, but for obvious reasons, so it's not that interesting. So I had three constructions for toposes, right? With one, the Boolean valued or Heiting valued, I showed continuum hypothesis is independent. The effective one, as I said, the classical part is just set. It is not interesting for classical word. It works whenever you want to do something about intuitionistic, or you are sensitive to extract some computational data. The sheaf one that we had millions years ago, the last thing is that I want to use the sheaf one to prove the independence of axiom of choice, which is impossible to do with the others in non-trivial way.
What have you shown here? You've done this construction, and you said with this
Principle, like, yes.
So this is showing independence or consistency of something?
It proves independence of something, and independence of something is the negation. So BP is false when you think classically, right?
Okay, this is showing, say, consistency of BP
with higher order Heiting.
This is what you need to show.
Yes. Yeah, that's the goal of this game. It's similar to the church thesis, right? So classically wrong, intuitionistic possible.
In this structure,
Yes.
Brown principle of evidence, church, extended heritage.
Yes. Yes, and so many other things. All of them are true at the same time. Every weird thing.
You're showing consistency with intuitionistic logic.
Yes.
So there's sort of one step less to do in terms of obligation.
they mean. So the point is that classically they are inconsistent, right? So therefore, you cannot do your double negation tricks. It is really important that these existential things are really intuitionistic. If you change it somehow to equivalent classical ones, then they lose the meaning. Yes.
One can imagine doing some extra step to show consistency with counter.
No.
Maybe not in a particular case, or not at all.
Yeah, sometimes you can, sometimes you can't. So for continuum hypothesis, for instance, we did, right? The whole thing is intuitionistic. We did your double negation trick, but these guys are the real essence of being, broad principle or whatever is really constructive. So I cannot find something equivalent to it or something similar to that, such that it is independent from classical. I can, but it would be just ugly.
Sorry. When you were defining this effective topos.
Yes.
And you have the general effective sets X, the equality.
Yeah.
Do you actually need those for this construction, or can you really stick with natural numbers with equality?
It depends. If you are working with first order, then natural numbers is enough. If you are working with higher order, depending on how higher order it is, right? If it is n to the n, then yes. But then again, it could be so the thing that I mentioned is just for any f in n to the n. But there are also some principles, some things that you want to prove independence of, and then they go for all power sets of n, all the subsets of n. Then I need to have some sort of subsets of n, right? So the reasonable thing is just to do whatever you can do in terms of set theory, and then just go there and compute whatever you want. Yes. First, they are proved in the usual realizability kind of thing. I guess Truelstrad did that. So he generalized Kleene kind of stuff to higher order, etc. Yes, but then when was that? I don't know, 70, 80 something. And then this Highland kind of thing is also 70 something. This is the top. The effective topos came in 1970 something by Martin Highland. But the point is, it is not just for independence, right? That universe is kind of very interesting in its own. So if you, for instance, if you have any topos with some natural numbers object, then you can mimic the usual kind of trick that we construct Z and then Q and then R. So if you do this, then you get constructive analysis here, which is interesting, one thing. The other interesting thing about effective topos is that there are some way to do sheaf theory via this effective topos. If you do that, then the continuous data of sheaves, which we have over set, etc., becomes just the Turing degrees. So there are some deep connections. Yes.
Does this look
No, it says, let's say that it is just a uniform way to address realizability, all different types or different arguments at once. One, two, since you are doing everything via topos theory, and interpretation in topos theory is just one, not different. So you are unifying the forcing, the Boolean valued kind of arguments, the realizability, all of them are the same thing. It depends on what topos you're applying things. But in any case, you are constructing just some new topos, right? So it's just the unification of every possible kind of independence that we know, except some complex things like iterated forcing or whatever.
Question. So there were something like constructive or intuitionistic set theories.
Yes.
So how are they connected with these effective toposes?
Or even more. So you can use toposes to construct models of IZF, which is the IZF. It is just ZF plus just intuitionistic, and you have to change some axioms because some of them are just really classical. You have to. Yes, choice implies classical, so you have to kill choice first. And then also the axiom of foundation is just very non-classical. It's like the minimal element, right? The existence of least number, whatever. You have to change it to epsilon induction, and then you're fine, more or less. IZF is just the biggest possible from and then you can use toposes to construct without that double negation trick. It would be just modeled for IZF. Of course, you have to do some tricks like that V constructing V alpha thing that I had, but then that's fine. So if you do it for that Boolean value, the heighting value in this case, then you get some heighting valued models of IZF, which is more or less equivalent to cheap key models of IZF. If you do this effective topos, it is equivalent to the realizability models, which are very famous for IZF. And then you can use it to prove independence from IZF. Kind of the same thing in another clause.
You go from ICF to campuses or something like this, or it's one way.
No, it's not that one way, but IZF is just kind of too, powerful. You have to change it a bit. There is some set theory equivalent to topos, right? You can do topos theory in terms of set theory, but you have to change your set theory a bit in power and presentation. But yeah, there are some, I guess. So for instance, of course you can go this way and come back, but you lose information, right? So what I mean is just to capture the same thing. So for instance, as I said, in the set theoretical world, we don't have any foundation axiom or well-foundedness, right? But set theory has it. So if you go there from set theory here, then it's fine because you have more. But if you go from topos theory to set theory, then you don't have it, but you have to restrict yourself to well-foundedness, well-founded sets, something of that sort. But usually, so it is two ways. So you go and come back. So, thank you.
So do send